And good evening, everybody, and welcome to our second or third, I don't know what the count is, TWed of the fall 2019 season. Today we've got Oshani is going to talk contracts, and I advertised her project, but she didn't do a part of it. So we're like 6 weeks. We are short of streaming live, but we record this and we put it up on the TWed's World YouTube channel, so it's available. And we're using WebEx technology now to do that. Feel free to ask questions throughout the talk. That's fine. Take it away, Oshani. Thank you very much.
Yeah, thanks, John. Thanks for that introduction. So today I will be talking a little bit about my project on smart contracts, domain-based learning, and semantics. So I especially want to get some feedback on some of the ontology-oriented tasks that we did. But before that, I thought I should give an overview of the project so that you know where I'm coming from. So with that, I would like to acknowledge the team behind this work. So people at the top are the PIs of this project, and we're very fortunate to have Leon's PhD student Farhad with us, and have fantastic undergraduate students. We did a lot of good work for this project. So speaking of blockchain technologies, there's a lot of hype, right? So most academics seem to dismiss. So this nonsense. It's like vaporware. However, like my point of view on this is that my advisor was Tim Berners-Lee, the guy who invented the World Wide Web. So when he invented the World Wide Web back in 1989, what he invented was just a protocol, HTTP, that you can use to serve a web server, and a language to build websites, HTML. So when he invented the World Wide Web in 1989, he did not imagine the Googles of the world, the Facebooks of the world, Amazons of the world will exist. So there has been this big rise in the adoption of the web. So similarly, blockchain technologies, it may be we may be at the start of the 20, if not 50-year growth phase for blockchain technologies. So it's worth investigating what kind of problems there might be in these technologies, and kind of think ahead into innovative technological solutions. So that's where I'm coming from. And then I should also acknowledge or bring to light some of the decades worth of computer science research that's under the hoods of blockchain-based technologies, even though you might have heard about Bitcoin since like 2008, 2009. It's based on these three key technologies. So cryptographic identities, it's not the only identity mechanism that's available on blockchain systems, but there's decades of research on that. Consensus protocol and creating an innovative incentive engineering mechanism, that's also part of the blockchain success. And really, blockchain is nothing more than a data structure. The Bitcoin blockchain uses something called the Patricia-Merkle tree. It's a binary hash tree. So, I don't know what the big hype about a data structure is. And my personal interest is really in the decentralized application side. So decentralized applications can be created using a distributed ledger, combination of the three technologies that I mentioned earlier, and computer code, smart contracts. So there are many applications of decentralized applications. Cryptocurrency, it's the most famous one that we hear all the time. And if you have been following these ICOs, initial coin offerings, you probably have heard of hundreds, if not thousands, of different applications. And banks are even using these decentralized applications in traditional banking, like to trade, or not trade, like to fiat currency. Supply chain. So Walmart deployed a blockchain system to figure out, provenance of things on their shelves. So if a recall comes, let's say for E. coli, they don't have to recall all of their produce. They can recall just the shelf in their supermarkets. And healthcare, electronic data sharing, that's a big application, voting, property records, name X kind of application. So just to go to the meat of the research that I'm interested in, so I'm looking at the adoption of blockchain technologies. And when blockchain technologies become mainstream, we want to be able to idiot-proof the technology. So there are some key guarantees of blockchain technologies. It enables trustworthy data sharing, and these records are done, or these transactions are done in a tamper-proof manner. These smart contracts allow flexible and expressive logic to create any application. However, once the smart contracts are deployed, they cannot be changed. So the goal of this research is, first of all, by looking at a smart contract, can we predict that there might be some unforeseen or unexpected situations on that smart contract? Secondly, if we deploy a smart contract, by looking at the transaction data, can we detect that there might be an unexpected situation? And thirdly, if there is an unexpected situation, can we fix that thing without having to redeploy a smart contract? So this is the direction of this research. Now, let me give an example of unexpected situations. So one very big unexpected situation in the blockchain world right now are these lost keys. Now, if you use a banking application or your Gmail or some email application, I'm pretty sure at least once in your life you've forgotten the password, right? I had to deal with that many times because my parents forget their password.
You mean just today, or?
Yeah, so it's a pretty common thing. So when non-tech savvy users start using these technologies, we can expect more and more of such scenarios. In fact, it's already happening. So there's this company called Quadriga CX. It's a crypto exchange based in Canada. So the CEO of the company, he died suddenly, and he was the only one who knew the password to unlock all of their customer accounts. But that's over $145 million worth of cryptocurrency. The court case is still going on in Toronto, and even the FBI is looking at how to recover the money.
So it proves the security.
Right, yeah, it's very secure. But yeah, but if you can provably secure that you own these, money, these tokens, then you should be able to, recover that. That's my stance. And then there's this kind of funny and at the same time sad story from UK. This man, he mined some cryptocurrency when it was not a thing, like Bitcoin was relatively zero in value, and he forgot about that and he threw it away in his trash. And then when Bitcoin became a thing, he wanted to mine his hard disk from the landfill, and the city would not let him do that because of some environmental.
Would they have let him dig up a box full of? That's not good. I mean, maybe
the city would.
The city would not let him, because it's in the landfill right now.
No, I know, but if it was not 7,500,
correct?
it was the equivalent amount of money.
Then the city might have done it themselves.
Oh, I see.
And even still, in this case, the city would have a good case to go after it themselves, but not let him.
Yeah, if they can figure out their
Figure it out.
Yeah. Yeah. So, what I wanted to get at is that right now, between 2.78 to 3.79 million Bitcoins are already gone for good. Even I have lost some Bitcoins because I've gotten this that I got free with the public and private key pair. At that time it was worthless. Now it's worth, lots of money. Anyway, so this is a big number considering that there's only going to be 21 million Bitcoins ever to be in existence. So, so this is the problem that we're trying to solve. Yes, Shruti. It's economies. Like that's how the protocol is written. So whoever this Satoshi guy is, like when he wrote or they wrote that protocol, they said that there will only be 21 million bitcoins ever in existence.
Because they didn't understand economics and monetary theory. They thought that deflationary currencies were good.
Yeah, whatever their reasons is, yeah, I don't know, but yeah.
They were kind of stuck in the pre-Nixon era.
Okay. Not really. I mean, that's not the same problem. So IPv4, again, they didn't think that the address space will run out, so they created a new scheme. This is a little bit different because they had some economic reasons to create that. Yeah, I don't know the reason behind 21 million. So anyway, so problem with decentralized systems. So like in your banking application, if you lose your password, you can send the request to the system administrator, and if you can sufficiently prove that you own the account, you can recover your money. But in the decentralized system, there's no such central authority that you can complain to, right? So this is the problem that we're trying to address. So here's our idea, and this was actually published at the IEEE Blockchain Conference, and it's a very simple idea actually. So if you look at the public ledger, it'll have something like A sent B 1,000 coins, right? Most transactions look like this. If you take the account owner, A in this case, might know something extra about this particular transaction. So they'll know what was traded for this 1,000 coins. So A will remember, I bought a phone from B. And then the state partner B will also remember that side of the story. I remember A bought a phone from me. But other users, they can only guess, right? Maybe they bought a camera from B. So we leverage this information asymmetry between the trade partners and other users to create our protocol. So what we need to do is that first we have to create this account recovery proposal. The account recovery proposal has two things. It will have a statement. It will have this unencrypted sentence saying, A cannot access my account since a date. And then it will also have some proof with some specific information targeted to a trade partner. So in this case, A is targeting this particular proof to B. And if you know public key cryptography, you know that we can take B's public key, we can encrypt this, and we get this thing. So this is essentially the proposal. And now A has to create a new account. So now A becomes A1. She's very sad because she has no money in this new account. But she has, this information, this additional information about what happened. So she creates this account recovery proposal. And we have some chain code that accepts this proposal. First, it goes through this naive-based AMP filter to see if the statement is a legitimate statement or not. And that passes, it goes to a voting stage to do this proof verification.
So this is something done by B?
No, this is done by our smart contract.
Oh, okay.
So B doesn't do anything. Okay. This is what B does. So imagine one of these voters is B. So when B gets this proof, B gets the proof, and if he agrees, he'll vote for this particular account recovery transaction. And then once this proposal receives adequate votes, in our implementation, it's 2/3 of the votes, account is recovered, right? And then as a thanks to B, A will give some money. Otherwise, no one will vote. Why would they go to vote for account recovery proposal? So eventually, you see both A and B are happy. So
how many people are we talking about?
Right. So these 2/3 refer to the number of proposals that, or like proofs that A puts in.
Right.
So yeah, there can be, like hundreds.
What if there's only
One. Yeah, so then that's not a,
3?
even that's not. So in our, thing we set an arbitrary number. I forget the number, but yeah, it's not as low as that. So,
Have you thought about using probability of fraud?
we have not, and I do not know what that means.
So if someone, so first off, there's the probability that someone can get the transaction.
Yeah.
And then you have the, so if B, so A is trying to, so A1, actually a different person from A, is actually trying to steal an account of A.
Aha, we have a safeguard for that. So let me go to the next slide.
Before, just one, I had a question.
Sure.
So the legitimate statement is sort of the clear, there's.
The clear statement, not the encrypted one.
Okay.
Yeah.
So is this assuming that A has done transaction with a sufficient number of people?
Right,
Or does
yeah.
it all count? Okay.
Yeah, so we haven't run any experiments. So these are all
Okay.
like, made up numbers, made up, scenarios, right? So we haven't tested this out in the real world.
Okay.
So when we actually deploy it in the real world, we'll know like what these optimal numbers are, And to answer your question,
So if, for example, A had only ever done transactions with one specific B, then it wouldn't be possible to recover their account.
right,
Okay.
yeah, because then they could be colluding, right?
Yeah. Well, I'm wondering if there are a large number of colluders.
Right. Yeah, then, we have this veto transaction. So let me go through this one by one. So, yeah, overburdening trade partners. So, if you get multiple of these counter recovery requests, that's why we have a stamp filter. So it will only filter out, illegitimate, transactions or like statements. And then again, like we have the voting to verify the proofs. And then Jim, to answer your question, so if people are colluding, we can have the original owner veto that transaction.
Oh.
So they have access to the same information that the other trade partners have. And remember, like when you create a bunch of transactions, you can even include the original owner, right? Because the final transaction will have to transfer money from the old account to the new account.
Right. So the old account is abandoned.
Right.
How would they do?
So the old person is alive and well. So this is the, so there's a catch. So if that old account is abandoned, there's nothing in this proposal to prevent such a scenario. So then, other people could guess, like you're saying. But, if this is a truly malicious attempt at getting somebody else's account, then the original owner can come and say, I'm going to veto this transaction because, this is an attack on my account.
So this is the real A, not.
Yeah.
Real A,
yeah.
A prime should be the same person anyway.
Yeah, but for other, people, like they are different, right? I mean, they have different addresses. So,
Right, if they're, yeah.
Yeah.
So I guess if A shows up with a.
But are you
So if they've got locked account, they don't have access to it,
Mm-hmm.
and they attempt to. So someone's trying to steal it from them.
Right.
I can see in the case where if they actually have access to it, they can veto it.
Right.
But if they don't have access to that account, which is the whole point of it in the first place.
Right.
Say that guy in the landfill has a bunch of Bitcoins. I dig it up.
Right.
And I start trying to guess transactions off of it. And I collude with some other people that he transacted with.
Right.
Then he's not going to be able to veto it because he doesn't have the key.
Right, you're right. However, if you have to collude with multiple people at the level of, you're right. Like if you collude with enough people, then they can, recover the account.
Right.
But our assumption is that this is maybe not a really good assumption. Like this is an honest faith attempt, and if they have to collude with that many people, then like
A dozen people.
Huh?
A dozen people with it.
Right. So we haven't, we don't know the number. So it's good to run some experiments and see what's a good number.
But the idea is to make that conclusion
Difficult. Yeah. Very
Right.
expensive. Yeah.
Right. So what I was thinking actually is that if you use rather than doing hard fractions or hard numbers, you compute the probability of fraud across a number of attempts to guess it, to basically answer the question. You can actually get a number that someone satisfies 9%.
Right.
That it's okay.
So something like peer prediction. So yeah, we explored that idea a little bit, how likely is somebody else to say that this is a real thing. So we had one proposal where we used peer prediction to decide the amount that will be rewarded to you or to a voter. But ultimately, we ended up in the implementation. We have just equal divide among people who voted yes.
Let's let Oshani kind of cover more.
Okay. So we have implemented this initial version of the system. So I don't know how much you can see at the back, but here are a bunch of, this was actually implemented in Hyperledger Fabric. So we have a bunch of user profiles. This first thing is the old Alice. So they all have, simplicity, they all have 1,000 coins. And then this new Alice, creates another account. And this new Alice puts in 200 coins as the reward for the recovery. Voters who would help her recover the account. Yeah, so those are these amounts. And when the recovery transaction is submitted, we create this transaction on the ledger, and then we initiate the pulse, and the votes are counted using these things called vote tokens. Yes, Neha.
So that's saying that this
Mm-hmm.
creates a new account,
Mm-hmm.
and this user is sent to all the people we had in transaction with, or there's just one transaction that this user is with.
So I just gave one example. So there could be other trade partners. So in this scenario, imagine A transacted with all these people, right? So A would create these proofs saying that, hey, Bob, I bought a car from you, or you can ask Chloe, hey, you got a house from me. You can create those transactions or so proofs.
So say that user has a bunch of minimum more than one, and that person is just talking to those people with whom they had this transaction.
Right.
So when we're looking at these votes, we're just looking at these votes whom this user A has connected.
Right. Yeah.
And not really.
Remember, it's initiated by user A. Yeah. The system only facilitates that process. Shruti, did you have a question? Right. Yeah. It is a distributed consensus problem. Yeah. Not really, but Paxos is one of the implementations of, I think Ethereum has one implementation of Paxos, but this is not Paxos. Matt, did you have a question? I know your hand was up earlier.
Yeah, I'm not sure if I got a lot about all of this, but I was just curious. So the voters B, they're incentivized to vote yes, right? Do they have any incentive to vote no or vote truthfully?
Right. Yeah. Yes. So if we can actually, that's not implemented in the system, and that's a very good point. So if in future iterations we can figure out these bad patterns of a user, like if they always say yes, maybe we can have
Would they count as less maybe their vote?
Right. Yeah. So, but that's a very good question, and yeah, we don't have a solution for that.
It makes collusion a lot easier.
Huh?
It makes collusion a lot easier.
Right. Yeah. Right.
And what is the, kind of related to that, what is the incentive of the system to get it right? Because, you've got there's a real Alice, and there's a fake Alice, okay? The account is gone,
Yeah.
okay? So either real Alice ends up with the money, or fake Alice ends up with the money. But the system doesn't lose anything, and the fellow members doesn't.
But they gain something.
They gain something if they don't count because they can still get it cut.
That happens.
Well, no, who gains something?
Alice.
In this situation, Alice the faker is trying to incentivize people.
In this case, we are assuming this is the genuine Alice who just had to lose their password. But if Alice is fake, disregarding the fact that we have a large number of colluders, Alice will not be able to gain access to the account.
The real Alice.
Or the fake Alice.
Or the fake Alice, yeah. If the voters say no, this is not a truthful attempt, then they would not vote yes.
Well, so I understand. So there's a moral victory. I'm talking about in terms of real losses.
Right. So if so let's say Alice is actually Alice. Alice knew it was actually Alice. If they unlock the account, she gets the money, and those other 5 people get.
Some amount so this
and
is.
Then
because she's put up the
award, yeah.
Right,
yeah.
and then if let's say that real Alice or fake Alice or Alice knew was actually fake, and they vote no, nobody gets the money, and nobody gets the reward. So it's lose.
But what if fake Alice puts up a reward?
That's what
I'm saying.
doing, yeah.
If she puts up a reward, and she gets it, then it's win-win, even if it's fake.
Right.
Same situation as if it were real.
Yeah.
And with too many fake transactions where they kind of that devalue the entire system, and so the currency value of the currency would go down, so they'd have some incentive.
No, these aren't fake transactions. These are fake explanations for transactions.
Real transactions that happen.
So Alice makes basically says to Bob, "Hey, I bought a pair of sneakers from you." Chloe says, "I bought sunglasses." David, it's TV. Yeah, and none of these things are true, but Bob, Chloe, and David all see the reward and say, "Okay," and there's no downside to it.
Actually, they don't see the reward. They just know that they'll get some reward.
Well, but there's still.
They don't know actually in our implementation they don't know that's why even though Alice put 200, not all of 200 is taken. So the algorithm the student implemented it arbitrarily takes some amount, some fraction of that reward and gives it to the.
So conversely, what so Frank votes false.
He gets nothing.
He gets nothing, but Alice still gets the.
Right, because 2/3 of the votes pass.
I would think that if there's a false vote, that would actually increase the probability that things are going on.
Right.
Because if in this case, I can convince 4 people to go in on you in a scheme to cover a fake account.
So you're saying all or nothing kind of thing?
Maybe all or nothing, or like I said, if you have a probability model of when things are real or not, and you could use an information theory approach to populate it. That would give you a better sense of, hey, there might be something going on here. Especially if the 4 of them have strong transaction interactions.
Right. Yeah. that's all the points. I saw some hands going up. Should I get going? If it's a quick question.
Just a follow-up on your answer. So, just like if someone is saying yes all the time, they might. So what if like that all those people who are asking me that actually so or we did have a transaction, then am I supposed to say no in between so that my vote counts in future?
So that's like extreme social engineering. I don't know a good answer to that. So yeah, somebody could, in order to, although like if others say, this is a legitimate transaction, and if you're the only one who's saying no, then that could be counted as like a bad behavior or bad profile.
Well, so that's an interesting point. If there was so in this scenario, Bob through Frank are being nominated, right? They're being nominated by Alice.
Yeah.
But what if there was?
And we also verify that these transactions are there in the ledger. So.
Right. So to make my point though is that what if the way you're doing it is there's a larger of endorsers, and you are selecting at random the actual endorsers that you use or you're going to consider. So
right.
instead of
going with just the people that you propose, you have a subset of the
Right. And
that's
that
a good proposal as well.
dials into the probability stuff a lot better than this.
Right. Yeah.
Yeah, because if the algorithm chooses the user, then you have to explain what the transaction was.
Right.
And then the other person has to agree that that's the case.
Right.
That will decrease the probability.
Yeah, that's a good suggestion. All right. Okay. So.
Yeah, you have a knowledge representation.
Yes. So I haven't.
The punchline.
Yeah. So should I go straight to that? But yeah, let me say so that's just a specific example of a unexpected situation. So we looked at the general process for strengthening smart contracts. So in that, we look at a smart contract. Smart contract, has essentially some assets with some attributes, participants with attributes, and some logic, right? So we look at that using a preprocessor, and we create something called an action list that operates or that executes in a privileged environment. So we need some kind of voting. So this voting is a little bit different to the voting that we saw earlier. So when the voters decide that this is a legitimate thing, we can execute that particular function. And, that's how we propose to do this generally, using smart contracts. And then you can imagine some cases where if you get inundated with these vote requests for something very similar, you're going to get vote fatigue. So for that reason, we use the learning mechanism to learn the voting behavior of an individual. So this learning data is part of a participant, so it's like an agent that's working off-chain. And in order to learn preferences, we use this Thurston-Mosteller process. So there we characterize the unexpected situation of the feature vector, and then we learn this parameter beta that tells us how likely this person is going to accept or reject the proposal. So we have this adaptive kind of smart contract. I'm kind of putting up so that I can get to the ontology part. So then we thought, okay, we are able to incorporate these learning mechanisms. Now, how about ontologies that are implemented as oracles? So there are two approaches for that. First one is we can actually characterize these unexpected situations in an ontology. So there are multiple reasons for doing that. First is to share common understanding of the structure of an unexpected situation. And second, we were focusing on one platform. And if you want to characterize unexpected situations in another platform, we want it to be interoperable. So we were working off of Hyperledger Fabric, but there are systems like Ethereum, IOTA, and then if it's a voting process, we want to figure out who gets to vote. And then the second line of thought is that without relying solely on the smart contract, can we use external rules to augment the smart contract logic? So this sequence diagram is a very simple one where we say, okay, a smart contract, when it executes, it can check for the oracle for any sufficient necessary conditions, and then use those things to execute the logic. Now let me start with the first thing, this ontology for characterizing unexpected situations. So we started on this and we realized that this is actually much harder than we thought it would be, because we're talking about unexpected situations. Even in a constrained environment like smart contracts and blockchain, it's
Usually expected.
yeah.
Unexpected.
Yeah, but we started on that. Yeah. So the ontology that we created, it's able to answer questions like what is the type of unexpected situation. So remember, this is when an unexpected situation happens. We are trying to model that situation based on the information that's available in the smart contract, in the ledger, or the participants, for example. So yeah, what are the assets or global resource in question? So yeah, we have this ontology available, and we plan to improve this obviously.
So next up, probability ontology for context.
Yeah. Right now, I don't have a good answer. We just created the ontology. We haven't really instantiated the smart contracts using this ontology. So yeah, we can use reason based on how we structure the knowledge. But yeah, this is just an initial attempt at characterizing unexpected situations.
How much of this was kind of informed by basically the structure of smart contracts in general?
Yeah, it's so what we have is based on blockchain systems have this layered approach, right? So you can go very deep, or you can go at the application level. So we kind of stuck at the top and the middle layers. We can look at the block state as well as we can look at the application state. So things of that nature. And by no means this is comprehensive. This is still ongoing.
Well, my so this at first glance this looks very daunting. But what I think just how much of this is kind of map architecture into ontology, and then add the extra bits about unknown, unexpected situations and stuff like that.
Yeah, actually there are ontologies like that. So there's Blondie. I forget the long form, but there is an ontology that characterizes these layers of blockchain technology. Okay. I don't know if anybody uses that. So this is very specific to unexpected situations. Okay. Yeah. Maybe, I don't know. Quite possibly, yeah. Yeah, I don't know the authors. I looked at it once and then I realized that it's not really what I'm trying to do. So I just didn't follow up after that. But yeah, if you have a resource from John, for me, I think you sent me some right last year. Should take a look. Okay. Yeah. So then something that we did implement to some extent is to leverage these external logic to execute the smart contracts. So the idea is if there's a gap in the smart contract logic, because this oracle lives off chain, not anybody, whoever is authorized to change or update that oracle can go and make changes, and then that new change will be a transaction on the ledger, so that we get a new hash for that particular oracle. So when the smart contract executes, it looks at the last known valid hash of that oracle against the current hash of externally available oracle, and if it matches, then it will execute the relevant rules on the oracle. So let me give an example. Decentralized course selection. So now this is the start of the semester. Students are taking courses. Just imagine that we have this made up, I have this made up smart contract where first day seniors can register for the course, second day juniors, and so on, right? However, you get all these exceptions. I mean, professors give exceptions all the time. So if a freshman comes with a very good GPA, the professor might give permission to register for the course on the first day itself. However, our smart contract does not have a proper function to execute to make this transaction happen. So in order to model the scenario, just imagine we have course selection ontology. So this has all the usual culprits in a university setting. And then we have this initial rule that has scenario I mentioned on the first day, seniors and so on. So the professor or whoever the professor dedicates his work to can go and update the rule and create a new transaction on the ledger. And now the rule is able to run, and the instance graph will look like something like this, so that the student can now add the course. So that's pretty much the ontology-based, smart contract execution that we worked on, and we have this very toy example, and we are currently looking at, kind of real-world examples to really, motivate this work. Yeah. Previous to this, okay. This one? Oh, it's not used here. No. So here, this is a kind of a different, scenario. So we are saying that we offload some of the smart contract execution logic to an oracle. So the scoop thing is to characterize an unexpected situation. Can you use scoop to characterize the unexpected situation here? Yes. But we thought let's try to get the rules running off chain. So for that purpose, I think this is the main meat of this particular work.
So okay, so now this is now one-off updated rule. This is consistent updated rule. This is how it is now.
Right. Yeah.
Okay.
Yeah. So with that, I think I can summarize the work I am doing in the Scales project. So given a smart contract, we can characterize unexpected situations using that scoop ontology. We have this smart contract processing engine that outputs action lists, and we utilize some machine learning techniques to learn the preferences of the voters so that the burden on the voters are lessened a little bit. So because this is a collaboration with Lirong, who's an expert on computational social choice mechanisms, he guides me a lot on this, group decision-making kind of work. So if there's one thing you want to take from, this presentation, is this, the end goal is to avoid smart contracts doing this to us in the future. So imagine you go to the doctor and you say to the doctor, I need urgent attention. And the doctor here is not the patient's primary care provider. And, if the doctor says, I'm sorry, I do not have access to your data, so you have to take these expensive tests and I have to delay your treatment, just because your records are, protected by a smart contract, it's not really a good thing. But because smart contracts are developed by human beings and we all, program, right? So we all make mistakes. But the thing about smart contracts is that once it's deployed, it's hard to change. It's actually impossible to change. So yeah, that's the goal of this work. So this is the takeaway. And then, if you're interested, here are the papers from which I borrowed materials for this particular presentation. If you're interested, let me know. I can send you these resources. I think I once sent it to at least their brush list when I did that oral. Yeah. So this presentation is available at this link. And I think I know everybody in this room, so feel free to contact me if you have any questions or if you want to collaborate with me on this project. And I have one student here. Hi, Roman. Yeah. Okay, so if you have any further questions, I'm happy to answer
So
them.
let's thank Oshani first. All right, questions. Quite a publication history in
Okay, 3 conference, 1 workshop.
These, so the bulk of this work, so you had students working with you last summer.
Yeah,
Right?
spring and fall.
And this.
Yeah, and I didn't get the grant this year. But I do have some students, like, from again. Okay, so no questions. I guess I was very clear. Oh,
My question is more kind of general. You don't have to flip back.
okay.
So when you were talking about lost
Any kind of currency.
so that you were kind of generically lost.
Some asset, some token.
Cryptocurrency.
Yeah, something. I don't really care because, I'm not a cryptocurrency researcher, so I'm only interested in the mechanism by which, recover.
Yeah, I know. You were using that as an example.
Right.
I was just kind of
Yeah.
I'm curious. You've got Bitcoin.
Right, yeah, there
But
are
they have
thousands of coins out there.
But they all have a similar thing. They have fixed total deployed value.
Mm-hmm.
That, so they all
Yeah.
probably have this similar problem where there's loss.
Right, yeah,
Lost value.
yeah. If you forget or if you lose the private keys, that means you don't have access to that account. So, people have different techniques for that. So if you have an Ethereum account, they give you this very large, phrase, like a paragraph that you have to remember. I don't know the number, but if you remember, let's say 5 out of like 15 of those words, then they'll recover that account. And there's this other scheme where you can do key sharding, meaning like you have a key, like I give my friends and family like a portion of the key. So T out of N, like 3 out of your 5, people who get together, they can recover my account. So there are various schemes out there, but that requires some kind of premeditation. Like you have to kind of expect that to happen in a way.
The other question I had is, so when we think of smart contracts, analog, and how real contracts or other real formal legal instruments
Right.
deal with unexpected.
Yeah, you
situations.
can go to a court of law and get the thing repudiated, right? But here there's no such court of law or like central authority that you can go because it's
Right.
supposed to be decentralized.
But there's
unless you
evidence that
change
has to
the-
be presented.
Yeah.
It's a different sort of
Yeah.
thing. But sometimes it can be very tedious, like such as power of attorney.
Right. Yeah.
We had a situation in our family where wife's power of attorney for her mother was validated because it hadn't been exercised. Granted, before my mother-in-law was sick and everything, but it was some time ago, bank validated because it hadn't been sort of, what's the expression in Linux, it hadn't been touched. And I had to go through the whole process to offer up this evidence.
Yeah.
Question that on. I don't think there are any more questions. So, well, thank you again.
Okay. I finished before time. At the rate I was going, I wasn't sure if I would